So we're talking, we're just picking up, I think, this is the end of chapter 6, and then we'll get to the beginning of chapter 7. This is about Fermat's little theorem and Euler's theorem. So we'll go here, and maybe we should start on a fresh page. Okay, so Fermat's little theorem. Fermat had a lot of theorems, I guess. I know about Fermat's last theorem. I don't know what Fermat's big theorem would be. Fermat's theorem is based on a prime number. So let P be a prime number. And A is just any integer. So it's any whole number. Then it's true that A to the P minus 1 is congruent to 1 mod P. All right, so let's just look at some examples. So I computed a bunch of these before class. We'll try various A's and P's here. And here's A to the P minus 1, and then A to the P minus 1 mod P. So what if A is equal to 3 and P is equal to 7? Then 3 to the 7th power is 729. And then if you reduce that mod 7, it turns out to be 1. Let me just show you how I'm computing those in case you're curious and you want to play around with it. You can do, even though we're not using Python for this class, it's still really useful for dealing with great big numbers. So you could do 3 to the 7th power like this, and then 3 to the 7th power mod, oh, sorry, it's 3 to the 6th, right? Sorry, that was a mistake, because it's P minus 1, so it's 3 to the 6th. Mod 7 is 1. So let me go back to this thing here. So this is actually, yeah, 3 to the 6th power is that. So we can do 2 to the 11th power. So this would be 2 to the 10th power, which is 1024, and then mod 11, this is 1. We could do 4 and 13, and then 4 to the 12th power is 16777 and then modulo 13, it's 1. So this is just some experimental evidence here. We will prove this eventually, but not today. It turns out it's easier to prove a huge generalization of this fact than it is to prove the fact itself. So we'll prove it when we get to Lagrange's theorem, which is a generalization. So this, what good can you do with this? One thing that you can do with it is compute inverses. So if you want to find A inverse in ZP star, so this is the multiplicative group mod P, we already learned how to do this last time using the extended Euclidean algorithm. But it's also true that A to the P minus 2 times A is the same thing as A to the P minus 1, which is going to be congruent to 1. So it's always true that modulo a prime, A inverse is congruent to A to the P minus 2. So we could give an example of this based on these examples that we did above. If you're working in the multiplicative group mod 7, and you want to know what 3 inverse is, this must be congruent to 3 to the 6th power, which is 5 mod 7. And then you can just check that it's true. So it should be true that 3 times 5 is 1. So 3 times 5 is 15, and modulo 7, that is 1. So it's true, works. Let's do maybe, I don't know, I have 3 examples here, but let's just do maybe one more. So if you're working in the multiplicative group mod 11 and you want to know what is the inverse of 2, this should be the same thing as 2 to what power?
Would it be 2 to the 10th?
Yeah, so the rule is, I should have written the rule. Oh, here it is. A inverse is a to the p minus 2. So what is 11 minus 2?
9.
9. Yeah, 9. So it's 9. So this is congruent to 6 mod 11. And now we can just check it out. So is it true that 2 times 6, what is that? That's 12. But modulo 11, that's the same thing as 1. Let me just give you one to do on your own. Let's see who can do this first. Might want to open CoCalc. So in Z13 star, try to find the inverse of 4. So what is the inverse of 4? And should we wait a minute for people to do this? I'll give you a couple seconds.
Would it be 2 raised to a power since it's 4 we're starting off with?
Yeah, so you could definitely use powers of 2 to do this. So what power of 4 is this going to be equivalent to because of this formula?
To the 11? Yeah.
Yeah, that's right. 4 to the 11th. So you would need like Python or some really big calculator, I guess, to figure this out. Unless you happen to know what 2 to the 22nd power is, which I don't think even computer science majors know. So somebody who might be a real freak. I certainly have no idea. So with the calculator, it turns out that this is 10. And now you can just check that it works. So is it true that 4 times 10 is 1? So 4 times 10 is 40. And modulo 13, 13 goes in evenly to 39. So this is 1 mod 13. So usually using XGCD to compute the inverse is faster, but certain computers have hardware accelerators for exponentiation. Like the book anyway says that like smart cards on like smart chips on credit cards have hardware acceleration for exponentiation. So in that case, this method of computing the inverse might actually be faster. All right. Now we're going to generalize Fermat's little theorem to a case where P is not prime. So we had the restriction with all that stuff that P is prime. So the person who generalized this is Euler. So let's kind of like restate what we just did. So we're talking about ZP star. So the cardinality of ZP star turns out to be P minus 1. Let's just give an example to see why that's true. Let's look at Z5 star. I'm going to make that more obviously a 5. Okay, Z5 star. This is all the things, all the integers less than 5 that have GCD 1 with 5. So the only thing that fails is 0. So you get 1, 2, 3, 4. So everything has, all of these have GCD 1 with 5, no factors in common. But we throw out 0. And so it turns out that there is 4 of them, which is P minus 1. And so that's always true because you have P numbers less than P, but then you throw out 0, so you have P minus 1 of them. Okay. So one way to understand what we just proved is that when P is prime, it's true that A to the, it's true that A to the cardinality of ZP star, which is P minus 1, is congruent to 1 mod P for A in, for any A in ZP star. Okay. So let me, I'm going to copy this and then take it to the next page. I wish this thing kind of would just go on continuously forever instead of dividing into pages, but I guess it works the way it works. Okay, so here's what we have. All right, So now let's say that n is not necessarily prime. N is any integer. So this is ZP star. Let's remind ourselves what Zn star is for n that is not prime. Like let's take something that's not prime, like 10. So what is Z10 star? It says all the integers less than 10 that have no factors in common with 10. So 1, 3, 7, 9, and that's it. Okay, everybody agree? And the reason I didn't write 0 is because 0 has a factor of 10 in common with 10. 2 obviously has a factor of 2 in common with 10. 4 has a factor of 2 in common with 10. 5 has a factor of 5 in common with 10. 6 has a factor of 2 in common with 10. 7 got to go in. 8 has a factor of 2 in common with 10. And so all of these were not allowed to join. So what this star does is it restricts you to numbers that are relatively prime to whatever number this is. And the advantage to doing that is that you get something that's closed under multiplication. You get a group under multiplication. So every element has an inverse, and it's a group. Okay, so it turns out to also be true. Oh, do you remember this fact? We talked about this last time. The cardinality of Zn star, this function has a special name, and it's called phi. This is the Euler phi function. And we played around a lot with the Euler phi function last time. Just to remind you of the most important property of the Euler phi function for us, it is if n is a product of primes p and q, then phi of p times q is p minus 1 times q minus 1. But we can actually apply that to figure out phi of 10, because phi of 10 is phi of 2 times 5. So what should that be according to this product here? I'm sorry, I can't stand the suspense. I have to answer it myself. It says 2 minus 1 times 5 minus 1, which is 1 times 4, which is 4. We already knew it was 4, right? Because we had...
That's the cardinality of that set?
Yeah.
That, okay.
That's right. And yeah. So it's the number of numbers less than n relatively prime to n. Okay. So let's come back up here and then maybe make a little bit of space. So I had written down this version of Fermat's little theorem. So here's Fermat's little theorem. So Fermat's little theorem requires A to be a prime number. And the generalization, which generalizes this away from the requirement that P is prime, is called Euler's generalization of VLT. But we'll just say Euler here. And what Euler's theorem says is A to the cardinality of Zn star is congruent to 1 mod n for all A in Zn star. Okay. So it's a little bit different because now this doesn't apply to just, so Fermat's little theorem applied basically to any A, but that's just because any A is in ZP star because P is prime. But this only applies to the A that are in Zn star, so it won't apply for certain things. Let's give some examples here. Let's just stick with n equals 15. Okay, so we know that the cardinality of, stick with 15. I guess we'll start with 15. Sorry, I got confused. So what is the cardinality of Z15 star? It's the same thing as phi of 15. Can somebody tell me what that is?
So those are all the numbers, all the common factors.
Yeah, this is Z15 star is all the numbers between 0 and 15 that are relatively prime to 15. So let me just write them all down and then we'll strike out some of them.
Is it 8?
Yeah, 8 is in
it's
there.
8. That's right. 8 is the answer. And we'll see why in just 1 second. And 8 is also in the 12, 13, 14. And now we go through with the red pen and we cross out everything that has a factor in common with 15. So 3 goes, 6 goes, all the multiples of 3 go. And then all the multiples of 5 go also. So 5 and 10. So how many does that leave? That leaves 1, 2, 3, 4, 5, 6, 7, 8. Another way to do this is to use the formula because 15 is 3 times 5 and they're both prime. So this is also 3 minus 1 times 5 minus 1, which is 2 times 4, which is 8. Okay. All right. So now let's just try to sort of verify Euler's generalization of Fermat's little theorem. So let's let A be equal to 7. So that's okay because 7 is in here. So what is 7 to 8? So 8 is the number that the theorem applies to. It's the cardinality of the multiplicative group. So 7 to the 8th power turns out to be equal to 5, 7, 6, 4, 8, 0, 1. And so this turns out to be equal to 3, 8, 4, 3, 2, 0 times 15 plus 1. So it's congruent to 1 mod 15. Okay. And so that same fact will also be true for any of these numbers that are inside this group. So it will also be true that 2 to the 8 is congruent to 1, and it'll be true that that 8 to the 8 is congruent to 1, and 11 to the 8 is congruent to 1, and 13 to the 8 is congruent to 1, and 14 to the 8 is congruent to 1. But it won't necessarily be true for some number that I've crossed out, like 5. It may or may not be true for 5. Should we just check it and see? So now the promise does not hold for 5. So let's just see what happens here. So 5 to the 8th power is, let's go back to our little terminal, wherever that is. Where's my mouse? Go here. Okay. So 5 to the 8th power modulo 15 is 10. Okay, so it turns out not to be true for 5, but that's okay because the theorem didn't promise that. It's only true for the members of the group. By the way, there's a faster, it takes a long time to compute 5 to the 8th, and then reducing it mod 15 takes more time. So it turns out that there's an efficient way to do both of those things at the same time. And there are fast algorithms for what's called modular exponentiation, which I think you guys might have actually done in 204. Did you do that?
Which one's 204 again?
And when you took Math 204, did you do the square and multiply algorithm? I think you did something like it. Maybe not exactly, but there's something like the square and multiply algorithm, which we'll talk about soon, that's in the 204 curriculum. But this is this works in both Sage and Python. It is 5 to the 8th power mod 15. And so the advantage to using that function is because you can do it for ridiculous values. like you can never compute that power. You know, you could never compute this number to that power. It would just be absurd. But you can do modular exponentiation, no problem. Okay, so let's come back to the worksheet.
And instantly too.
Yeah, and it's super fast. It's like, how fast does it run? It's a logarithmic algorithm, so it runs in time proportional to the number of digits in the number. So
Like as best you can get.
Yeah, so those numbers were huge, but they were only a few digits long, you know, like 20 digits long. So it just takes a snap of your fingers. All right, so that is Euler's theorem. And I cooked up some stuff for you guys to look at on CoCalc, but I think it's not quite time to go to CoCalc. Let me talk about a couple other things. All right. Here's just a definition. So the order of A in Zn star is the smallest positive integer k such that a to the k is congruent to 1 mod n. So let's just explore this a little bit. And I didn't prepare to do this, but we can figure it out.
Is that what we were doing on the other page?
Yeah, kind of. So what we showed that in the previous page, when n is equal to 15 and a is equal to 7, we showed that 7 to the phi of 15, which is 7 to the 8th power, is congruent to 1. But what you'll find is if you start computing the powers of 7 mod 15, so I'll do this for you in a second. So we've got 7 to the 0th power, which is 1, is congruent to 1. But 0 is not a positive number, so this has to be positive. So let's keep going. So 7 to the 1 is 7, which is just 7. And then 7 squared is 49, which is what mod 15? 15 goes into 45, so that's 4, right? Yeah, great. Okay, and I am not able to mentally do 7 cubed, but it doesn't matter because I can do 7 times 7 squared. This is congruent to 7 times 4, which is 28. And then what is that mod 15?
13.
13, yes, that's right. Okay. Okay, so 7 cubed is 13. And now I definitely don't know what 7 to the 4th power is. But this is the same thing as 7 squared squared. So it's congruent to, from this line, I can see that 7 squared is 4. So this is 4 squared, which is 15. No, sorry, it's 16, which is congruent to 1. Okay, so that means that the order of 7 is 4. Because 4 was the smallest positive power that made 1 come out. So I was just looking for the smallest positive k such that a to the k is congruent to 1. So in the case of 7, this is 4.
So for that example, like 7 is A and 4 is K?
Yes, that's right. And what you would find if you kept going here is it would just start over again, because 7 to the 5th is now the same thing as 7 times 7 to the 4th, but 7 to the 4th is 1. So the pattern begins again. It will keep going like this. 7 for 7 to the 7 is 13, and 7 to the 8th is 1. So it just keeps going like that. So there's a pattern. It goes 1, 7, 4, 13, 1, 7, 4, 13, 1, blah, blah, blah. So one way to understand what Euler's theorem is saying is just that in this cycle, so every element will always fall into a cycle like this, and what Euler's theorem is saying is that when you get to phi to the n, you'll always be on something that is 0 with respect to the order. I guess what another way to say it is that phi of n is congruent to 0 mod k, where k is the order of any element.
Is order kind of similar to, like, back when we talked about LFSRs, we talked about period?
Yeah, that's right. There's a period here. Each element has a period, which in this context we call the order. That's right. It's a good observation. And so what Euler's theorem is saying is that the order, maybe period would be a better word, but the order divides the cardinality of the group. So another way to understand what it's saying is that k divides phi of n. It's the same thing as phi to, what does this mean? This means phi to the n is equal to some number L times k. And so that also just means that k divides phi of n. So there's a further generalization of all of this stuff called Lagrange's theorem, which I wasn't going to talk about, but we accidentally got right there. And Lagrange's theorem says that for any finite group, G, and for any element of that group, it's true that the order of A divides the cardinality of the group. And so it ends up being true that A to the G is the same thing as A to the, what is this, like L times the order, which is the same thing as A to the order to L. And so in general group theory, you know, we use this letter E to represent the identity. So this E, just think of it as being 1. So what the identity is and Zn star is 1, but now we're doing it completely abstractly for any group whatsoever. And so this is the identity, and just like 1 to any power is itself, the identity to any power is itself. And so this is true. And now this isn't necessarily a modular group, so I don't need to say mod whatever because it's just a group element. And I think I've really gone too far probably, so I'm not going to do the proof. But there's a beautiful proof of this, and once you prove Lagrange's theorem, it goes all the way down. So Lagrange's theorem, if you can prove that, proves Euler's theorem because this is an example of a finite group. But then once you prove Euler's theorem, that proves Fermat's little theorem, because Fermat's little theorem is just a special case of Euler's theorem where n is prime. You guys just did a lot of group theory in a short period of time. How do you feel?
That was like 200 years worth of number theory, all condensed into like 5 minutes.
Yeah, that's true. Yeah, we went through 3 different generations of thought, you know, from Fermat to Euler to Lagrange. So these are also like the smartest people that have ever lived, and it took like 90 years for them to get all this straight, and then we just did it in 30 minutes. So what don't you understand? It's kind of silly that you know, this happens all the time in math class. You go through like 100 or 200 years of hard intellectual progress in a couple of hours, and then it doesn't make any sense, and no surprise because it took.
I have a quick question about Fermat's. So why is that case special where the value is prime? What is that used for when p is prime? Besides just like the proof.
We're going to use it in the proof of the correctness of RSA.
Okay.
And we might get there today, so maybe we should just keep going. So the next topic is RSA. So let's just keep going. Start on a new page. So RSA was, or possibly still is, the most commonly used public key algorithm in the world. And it was invented in 1977 by 3 friends from MIT. I assume they were friends. They started a company together after this. And their names were Ron Rivest, Adi Shamir, and I forgot the first name of Adelman, but the third party here is Adelman. Adelman is a great name for a cryptographer. And so they came up with this public key idea, which we've kind of been like dancing around for a while because it's based on the difficulty of factoring n. You know, public key is all about one-way functions. So we've said going from p and q to n is easy, but going from n to the factors is impossible. So this is the hard problem that makes RSA work, and it was patented until the year 2000 in the United States. And so they made a lot of money off this. There's a company called RSA Labs. I think it's called Labs, and it was either bought. I think it was either bought or sold by Dell for billions. So all 3 of these guys are good candidates for being billionaires. And it's kind of like it's funny because this wasn't like a one-hit wonder for them. So these guys have also produced other amazing cryptographic accomplishments, like Shamir was involved in the discovery of differential cryptanalysis and outside of the intelligence community. There's also Shamir secret sharing. You've probably heard of the algorithm, the stream cipher RC4, that stands for Ron's code 4, which was invented by Ron Rivest, and there are lots of other examples. So these guys are like cryptographic royalty. They invented RSA, which is just named after them. Okay, so how does it work? So so there is a public, you know, so what makes public key public key? There's some kind of public information and there's some kind of private information. So we have, in the setup here, we have n is a product of 2 very large primes. So n is a product of 2 very large primes. And here, very large means like either 1024 bits or maybe double that, like 2048 bits. So then, you know, the number of bits in n will be twice that. So n could easily be like 4096 bits or even better, or even bigger. We gave a table earlier, which you can go back to in the book, that shows how many bits n needs to be before you get the equivalent level in symmetric key security. And I'm sorry, I've forgotten how big this needs to be to get you to like 128, but this is at least 128, I think. Is that right? I don't know. I think people are moving away from using 1024. So maybe 2048 for the primes is the place to start now. Anyway, I'm going on too long about that. So the public information here is n, and it's also this number e. This number e is called the public exponent. So everybody gets to see this. So that must seem kind of mysterious right now, but it's very non-mysterious because it's usually one of several different values. So these are the values that e usually is. So either e is equal to 3 or 7, or most commonly and maybe most weird is it's often 2 to the 16th plus 1. And so there are reasons that this is true. So this is like a 1 followed by a bunch of zeros. Don't know how many zeros I have to write here, like 15 or 14. So I might be slightly off here. But this is a number that's big but not too big, and it's mostly zeros. And we'll get to the details later. It has to do with the square and multiply algorithm. But the reason this number is commonly used is because it's big enough to make things spin around mod n. So that's a big enough number that if I take something like even a very small number like 8, and if I raise it to the eth power, let's say the e is this number, I want this to spin around several times mod n. So I don't want this to just be like if this were 8 cubed or something mod n, then the mod n doesn't do anything. This is still just 8 cubed, and so somebody could take the cube root of that number, and that's not a good thing. So that's why that particular number often shows up as a base. I probably tried to explain that too early. Okay, so that is the public information, and now what is the private information? So the private information is, it includes some of the public information. So n and e, might as well throw those things in. And it includes p and q, and this other number d, which we have not yet explained. And you could throw in phi of n. So phi of n is kind of equivalently secret to all of these things. And I'll say more about that in a second. But first, let me just define what d means. So what d is equal to the inverse of e, whatever e is, mod phi of n. Okay. And so I feel like all that was pretty confusing. So let's get to, but if you understood all that, now you're ready to completely understand RSA. Okay. So remember the basic idea with public key cryptography is anybody can encrypt, but only the person who knows the private key can decrypt. So that means that you must be able to encrypt using just the public key. So let's pick a message. So X will be a message. So a message is just anything in the set Zn with no star on it. So it's just some number between 0 and n minus 1. So once you have that, how do you encrypt it? So the ciphertext Y is X to the E mod n. Okay. And of course, this is the ciphertext should be secret. This is why you want E to be kind of big, because you want to make sure that when you do this exponentiation, even if X, in the unlikely case, is some very small number, you still want it to spin around mod n several times. It's just like spinning a lock on a combination lock. So, you know, if it doesn't spin around, then you can figure out what X is just by taking the eth root of Y. So you don't, that has nothing to do with, you know, modular arithmetic or anything. So you need E to be fairly big to stop that from happening. But usually X is itself a very big number, so it's not a huge issue. Okay, so this is the encryption. So now how do you decrypt? Well, only somebody with the private key should be able to decrypt. So it must involve one of these secrets here. And so the way you decrypt is, to get x back, you just do y to the d mod n. Okay, and so this yd is the same thing as x to the e to the d mod n. And so it turns out that this is always just x. So if you're wondering why in the hell is that true, that's a good thing to wonder. We haven't proved that. There's a long argument as to why that's true. But this is the magic that makes RSA work. It's x to the ed mod n is equal to x. So let's give an example. And to do the example, I'm going to go to CoCalc. Anybody have any questions?
Really?
I should have already had this set up. I forgot about it. Okay, so we'll go to crypto. Loaded pretty fast. That's good. And I don't think I actually gave this to you guys, but if you create, if you know, on CoCalc, you can always create your own Sage worksheet. So you could kind of do this yourself if you want to, and I'll give this to you later. So let's stick with RSA, okay? So hopefully you can see that, but let me make it a little bigger just in case. So just to prove that there's nothing up my sleeve here, maybe that's a little too big. I am using some random numbers. Sorry, oh man, I think I made it too big to actually work well. You're probably just about to vomit. No, stupid thing, don't do that. I don't know why it's jumping up it's jumping way up there. Okay, here we are. So these are like actually industrial strength numbers. So, and as far as we're using a good random number generator, which I'm not positive that Sage is, but let's say that it is, then P is going to be a 1024-bit number, and so is Q, and this should be like industrial strength. So everything that we're going to do here should actually really be unbreakable. So here we're using this fact we talked about before about the formula for phi of n. So in order to compute phi, notice that you have to know P and Q. We talked about this last time, that knowing that phi is equivalently secret to the factors of n. We talked about that last time. So it's believed that there's no way to compute phi without knowing P and Q. You can compute it like this using the formula. So now for E, I'm using this number that I talked about before. I have to make sure that that thing actually has an inverse. That's why I checked the GCD here. So I'm making sure that E actually does have an inverse modulo phi of n, because if it doesn't, then I need to change something. So D is just the inverse of E. So notice that E is relatively small, but then D just becomes a typical element mod phi of n, and so it's enormous. One other thing I tried to emphasize last class is that phi of n is basically just as big as n. And you can see why, because n is the product of P and Q, and phi is the product of two numbers that are just about as big. Okay, so now x is going to be our message. So it's just a random integer between 1 and happens to be this guy. That's what I meant when I said that x is typically fairly large. So we
There's an L at the bottom.
Oh yeah, that just means that's the data type. It's like long or something. It has to do with
okay.
Python data types. Yeah, it's confusing. Sorry. So y is just x to the power e mod n. So in this example, it turns out that y is equal to this huge number. So now just think about this. It's kind of fun. If you showed y to your friend, and as far as RSA is really a secure cipher, they would never be able to discover x. If you told your friend y, e, and n, they would never be able to discover X. And as far as RSA is a secure cipher. But we can easily get back to X because we know P and Q. So once you know P and Q, what can you do? If you know P and Q, then it's easy to compute phi. And if you know phi, then it's easy to compute D. And then with D, you can do the decryption. So here's the decryption. It's just y to the dth power mod n gets us back to X. You can see it's saying true because it actually works. And that's it. So I hope it was good to make the numbers that big. You could also, of course, you could do all this with like extremely small numbers, which might be better. Could change this to like, I don't know, something really small, like 2 to the 6th power, and do the same thing again. So I'm just curious here, what are N and P and Q in this case? Okay, so here's an example with smaller numbers. Then D turns out just to be 53. Y is 278, and decryption still works fine. And you could, if you really want extremely small numbers that are very easy to understand, you could just make this exponent even smaller. So in the last few minutes, I want to again talk about like things that are equivalently secret. Now we talked about this a little bit last time. Let me start on a new page. So the following are equivalent. One, that P is secret. 2, Q is secret. So I'm assuming there's the public information here, N and E. Everybody gets to know what N and E are. And phi of N is secret. And so it's clear that if you know P, then it's easy to get Q because Q is N divided by P and vice versa. And division goes quickly. If you know P and Q, then it's easy to get phi because phi is just P minus 1 times Q minus 1. And if you know phi, how do you get back to P and Q? You can do it because you have these 2 equations and 2 unknowns. N is equal to P times Q, and phi of N is equal, well, there they are, actually, right here already written. So these are 2 equations and 2 unknowns if you happen to already know what phi of N is. So you can just use simple algebra to figure out what P and Q have to be. So we did all this last time. These things are equivalently secret. But knowing all these things is equivalently, is equivalent to knowing D. So D is secret. So seeing why this is true is a little bit more complicated. So if you know one of any of these 3 things, then you know them all. And in this case, if you know one of these 3 things, it's easy to see how you can then know D, because D is just E inverse mod phi. So if you know any of these 3 things, then you also know phi of N, and then you just you know E because it's public information, and then you can easily compute D, which is the inverse of E mod phi.
They're all related to each other.
Yeah, exactly. But now if you suppose you know D and N and E, so how do you figure out one of those first 3 things? So the secret is to write down this equation. So we know that D times E is equivalent to 1 mod phi N. And so that means that D times E is actually literally equal to some number K times phi N plus 1. And now we're going to try to solve for phi N here. So we can do DE minus 1 divided by K is equal to phi of N. Okay, all right. so we haven't exactly, we can use this equation to figure out what phi of n is. And the reason we can do it is just because k is usually actually a pretty small number. I think there's some theoretical justification for this, but it's easy to verify by writing computer programs. You don't have to check very many k's to find the k that makes this true. And if you have a candidate for phi of n, it's easy to check whether or not it actually works, because you can you have lots of ways of checking whether phi n is true. You know, from phi n, recover p and q, and then check that their product really is n or something like that.
K
So
is K. I'm sorry, just to recap. K is the set. It's the cardinality set, right? Of all the.
Yeah, I was worried this would be confusing. So before we were using K to stand for order, but this is a completely different K.
Okay.
This is just because of the meaning of being congruent to 1. What does it mean? It means the remainder is 1.
Yeah.
So DE goes in, phi goes into D times E some actual number of times K. It goes in evenly K times with a remainder of 1. And actually, I'm glad you asked that, Aiden, because now I see why K is small. It's because, you know, D times E is going to be at most like phi squared, right? And especially if E is a small number. If E is a small number, then this is not going to be such a big product. You're not going to need that many. You're not going to need K to be very big to get up that high. Anyway, I put this on, I implemented it in Sage here. That's what this last thing is. So I set this up for when P and Q were the big industrial strength numbers. So this is like a real you know, attack here, if you want to call it that. So it's just trying a bunch of Ks. It tries up to 100,000 Ks, but you know, 100,000 is like on a computer, so it's actually not that bad. And I did this several times, and always you found K quickly. So for this last run, you can see it found K after about 50,000 tries. So finding K is not hard. And once you know K, you can just plug it into this equation here, and then you also know phi. And then once you know phi, you know all of these other things. You don't need to remember that argument, though it's good to know, but you should know that all 4 of these things are sort of equivalently secret. If you know any one of them, then you can easily figure out the other 3. Okay. So there are a couple of missing pieces in the story that we have to fill in. One is, how do we find 1024-bit primes? Because it seems kind of silly here, because we said earlier that in practice you can't factor a number with more than about let's say 800 bits. So how do we it takes some explanation here, this like process where we quickly find P and Q. You can see that it can be done because we just did it using Sage. It doesn't take very long, but if you just pick a random number, first of all, is there a decent chance that if you pick a random number that big that it will be prime? You know, because let's suppose that, you know, the primes get less and less dense as you go out in the numbers. So maybe by the time you get to numbers that are this big, the prime numbers are just too sparse to sort of like randomly pick one. But it turns out that that's not true. So the chances of finding, if you just pick a number that is like n bits long, or how about b bits long, the probability that a number that's b bits long is prime turns out to be about 1 over b. So to find 1,000-bit primes, you really just have to try about 1,000 times before you find one that really is prime. But once you actually have found a prime, how do you know that it's prime? Because you can't factor it. It turns out that knowing whether or not something is prime is not exactly the same question as what are the factors of this number. So there's a way to detect primality that is much faster than factoring. And so we'll talk about that at some point in time. The other the other kind of hole that we have in our story here is how to do x to the, or how about this, sorry, y to the d quickly. The way I phrased it is a little bit of a trick question because we don't actually need y to the d. We need y to the d mod n, which can be done much faster than just computing y to the d. Why does this naive version take a long time? It's because it's y times y times y times y times y times y times y. And how many product, I mean, how long is this product? This product is length d. But then what is d? D is about the same size as phi to the n, which is about the same size as n. So if you actually had to multiply all these things out, you would be doing it for the, until the heat death of the universe. But there's a fast algorithm for doing modular exponentiation called the square and multiply algorithm. Okay, which is how we do that. So that's what we're going to be doing in the coming lessons, and maybe I'll do this over spring break and just put it on YouTube so that we can catch up a little bit. The other thing we need to do is prove the correctness of RSA. So we haven't given any explanation of why this is true. And I'm kind of inclined to just go ahead and do it now, even though it's going to put us over time. It should be okay, right? Because I'm recording this. So if you need to go, please just go. And it's okay because we've already taken attendance. And if you have to leave without saying goodbye, it's okay. Just keep in mind that we don't have any official meetings next week, even though I will be putting up content and I'm free to talk if you do want to talk. Okay, so now I am going to prove that that this is true, that x to the e d is really congruent to n. We'll start on a new page. So we want to show that x to the ed is congruent to x mod n. Okay. So the proof is in the book. So I'll just be explaining it and answering questions if anybody has a question. So let's start with this fact that we wrote down before. So d and e are inverses. So that means that d times e is equal to 1 plus some number, which in this case we'll call t, times phi of n. This is just what it means to have a remainder of 1 mod phi n. So now that we have this notation, we can write x to the e times d as x to the t times phi of n plus 1. But this is the same thing as x to the t times phi of n times x. And what we want to show is that this is equivalent to x mod n. Okay, so now we have kind of a, I don't know, an easier problem to solve. So there are two cases. One of them uses that stuff that we were talking about at the beginning of class. So here's case 1. So case 1 is that the GCD of x and n is equal to 1. So this is the same thing as saying that x is a member of Zn star. So if you pick if you pick x at random, this is the case that you're almost certainly going to be in, because you know, zn star is just about as big as zn. There, you know, there's, sorry, you don't need a star in this last case. So these things are approximately equal size. So if you pick a random element of Zn, it's almost certainly also going to be a member of Zn star, but not necessarily. Anyway, so in this case, what is the good thing that happens? You get Euler's theorem. Euler's theorem says that x to the phi n, in this case, is going to be congruent to 1 mod n. So this is why we're studying Euler's theorem. Okay. So now that we know that, take a look at this expression again. So we have x to the t times phi of n is the same thing as x to the phi of n to the tth power. But now we know that this is equivalent to just 1 to the t, which is just 1 mod n. And so that means that this thing is just 1. So if that's 1, then it's obviously true that this times x is congruent to x. Okay, so we're done. So then it's clearly true that x to the t phi n plus 1 is congruent to x mod n. And this case is done. That was the easy case, and also the most likely case. Now here, let's do the weird case. So case 2 is that the GCD of x and n is not equal to 1. So we know that n is equal to p times q. So what could the GCD be? If the GCD could just be either 1, p, or q. So let's, it's kind of symmetric whether or not the GCD is p or q. So let's just say that it's p. So without loss of generality. Without loss of generality, the GCD, if it's not 1, let's just say that it's p. You know, maybe it's q, but then it'll just be the same argument with a different letter. So what does that mean? That means x is equal to r times p for some r. Okay, and so in this case, the GCD of x and q is going to be equal to 1 because p has nothing to do with, x has nothing to do with q. So this means that x to the t phi n is going to be congruent to x to the, this is actually take more work than I thought. Yeah, so sorry, I'm getting ahead of myself here. Okay, so this is equal to 1 mod q. So before I had thought it was obvious why this is true, but maybe it's not obvious. So let's figure it out. So it must be true that x to the phi n. So let's try to just show that x to the phi n is congruent to 1. So that must be why this is true. So x to the, oh, I get it. Yeah, because x to the phi n is the same thing as x to the p minus 1 times q minus 1. And this is the same thing as x to the q minus 1 to the p minus 1 power. And now by Fermat's little theorem, x to the q minus 1 is equivalent to 1 mod q. Okay, so that means that the stuff inside the parentheses here is really just 1. and 1 to the p minus 1 is 1. So that means that x to the phi n is equal to 1. And then this thing is the same thing as x to the phi n to the t, which we just showed is the same thing as 1 to the t, which is equal to 1. Okay, so we've shown that that's true. Sorry, it took longer than I thought. So now what can you do with this fact? We have that x to the t times phi n is congruent to 1 mod q. So now we just go back to real numbers. So that means that x to the t times phi of n is literally equal to 1 plus u times q for some u. Okay, because the remainder is 1 mod q, so let's just say that q goes in u times evenly, and here's the remainder of 1. So now multiply both sides of this expression by x. So you get x times x to the t phi n is equal to, so I'm multiplying in x. Maybe I should just do this slowly. So this is uxq. But remember that x is equal to r times p. So this is u times r times p times q. So this is the same thing as x plus ur times n. But here we just use the fact that p times q is actually equal to n. So now we can reduce this mod n, and this stuff that has a factor of n will just go away. So this is congruent to x mod n. So let's just write it all on one line. We just showed that x times x to the t times phi of n is congruent to x mod n. And this is precisely what we have been trying to show ever since this line up here, right? So way back here, this is what we're wanting to show, okay? So we just showed that this last equivalence is actually true. So x to the ed is equal to that, and then we just showed that that is congruent to x in either case. So both case 1 and case 2, that ends up being true. That means that x to the ed actually is congruent to x mod n, and that proves the correctness of RSA. Anybody still here?
I'm still here. Sorry, I was muted.
Oh, why? 18 people are still here. Oh my God, this makes me like weep with gratitude. Thanks for staying around. I'm gonna stop the recording.